In this video, we're going to solve exponential functions. We're going to learn about the concept of an exponent, how to graph those exponents, and then how to solve for equations that utilize x and exponents in them. So let's start with the concept of an exponent. Let's say we have 3 raised to the 4th power. What that means in terms of exponents is that we have this value of 3 and it is multiplied a total of 4 times together. So we have 3, which we call our base number, and then we have our exponent, which we have here is 4. So 3 as our base multiplied 4 times. 1, 2, 3, 4. So if we multiply that, we would get 9, which are these two values here, multiplied by another set of 9, 3 times 3. So then we can actually just multiply 9 times 9, which would be equal to 81. Now something else we can do is if we have, say for instance, the value of 16 and it is raised to the 1/2 power. So this again is going to be our base value, and we are raising it to an exponent of 1/2. So when we see something like this is telling us what value of 16, where you have two values which we'll just call x, would multiply and add up to 16. Now the reason why we have two values is because of this denominator of 2, meaning 2. If we had, say, something, say 1/3, that would be 3 values of x, x times x times x. And this can kind of help us solve some problems out. So what two values can you multiply to get 16? And that idea is going to be 4 times 4. 4 times 4 would be equal to 16. Now we've also seen this 1/2 in a different way. We also see this as what we call the square root function, like this. Well, another way you can write square root is actually going to be 16 raised to the 1/2 power. And you can actually put a 2 in front of here. You might see this in more advanced math books. But this also can be, say, where you have the cubed root of 27, which we would write as 27 raised to the 1/3 power. Now let's say we had 27 raised to the cubed root. That would mean that we'd have x times x times x. 3 values that would equal to 27. Well, that would be 3. 3 times 3 times 3, that's 9 times 3, which is equal to 27. Now another way that we can see exponents is what happens if we have a fraction. So say we have the fraction of 1/2 and it's raised to the 3rd power. When we see something like this, again, we still consider this our base. It's how many times are we going to multiply this out, which would be 1/2 times 1/2 times 1/2. Because we have 3 instances where we need to multiply that. But we can also simplify this out and also see this as 1 raised to the 3rd power over 2 raised to the 3rd power. So we can actually just take that cubed and put it on the top and put it at the bottom. So we can see this as 1 times 1 times 1, which is 1. 2 raised to the 3rd power will give us a value of 8. So again, another example of this will be, say that we have 3/7 and we raise it to the 5th power. Well, we would know that this would be the same thing as 3 raised to the 5th over 7 raised to the 5th. And then we can solve from there. And again, this concept can be applied to, say, if we're taking a value of 25 over 36 and we take it to the 1/2 power. Again, 1/2 is the same as square root, or two values that would multiply to 25. We'd have 25 to the 1/2 over 36 to the 1/2. We can simplify that to being 5/6. Now if we were to graph an exponential function, we can look at the parent function, which we denote as b raised to the x power. So if we were to do an example of f of x where we have 3 raised to the x, we could create a table, and if we had our table for x and y values, we can solve for -3, -2, say -1/2, 0, 1, 2/3, and 2. If we solve this all out, we would get 1/27, we would get 1/9, root 3/3, 1, 3, root 27, and 9. If we were to graph it, it would look something similar like this, where 0 will equal 1 as the parent function. And just to be clear, that will be for all parent functions, whether it's going to be 2 raised to the x, 100 raised to the x, or even a fraction of, say, 1/2 raised to the x. Anytime that x is equal to 0, your value for y or f of x will always equal to 1. And this can help us understand the full standard equation where we would have b raised to the x minus h plus k. So if we change our value of h, This will denote where we shift our value of that 0 and 1, where we can shift it to the left or to the right. So if we take h and we make it -3, we're actually shifting this value over 3 points to the left. So it would be here, and our graph would more look like this. Now if we had h is equal to, say, +5, we'd actually be shifting it over 1, 2, 3, 4, 5 values this way. And so our graph would look something like this. Now h, again, is going to be what we shift for the left and right axis, but k will be actually what we shift for y. So anytime we take this value of k, we're actually shifting that point either up and down on the y-axis. So if we have a positive value, say a 4, that value would be 1, 2, 3, 4, and it would be up here and looking something like that. Now there also is a multiplier which we can put out in front, which we call a, and a will either extend or diminish the slope at which this increases as it approaches infinity. And with that, we can actually talk about the domain and range of this function. Now domain is the values of x from -x to +x in which this function can be used. For any sort of exponent, that's always going to be from -infinity to +infinity, meaning that we can plug in any value of x and we will get an output for y. Now our range is actually going to be different. Now an exponent has something called an asymptote, but it will actually not be able to cross it. So we have an asymptote at y is equal to 0, meaning that if we approach it from the negative side, we actually see that we're approaching 0, but we will never actually get to 0. And we can think of this in terms of a function. You can never have a negative value if you are doing an exponent to it. The closest we can ever get is going to be 0. It'll get smaller and smaller, but it will never actually approach 0. And vice versa, as we go to more positive values of y, we're actually seeing that we will approach infinity for that, which again is our y values. Now we call this equation, as we go to infinity, we see this exponential increase. We call this exponential growth function, which we can use for solving word problems. Now say for instance we have f of x, and instead of being a whole number, we have a fraction again. And we raise that to the x power. Now let's say for instance that we have f of x, and instead of it being a whole number, we have a fraction for our base value. So if we were to do a table of x and y, and for x values, we plug in -3, -2, -1, half, 0, 3 over 2, and 2, we would get values of 27, 9, √3, 1, 1/3, and 1/9. And this graph will look something like this, where again, at x equals 0, y will equal 1. Now this follows the same standard equation that we saw previously. However, there's going to be a little bit of subtle difference in the shape of the graph. So again, if we change our value of h, that actually will denote what we're changing for our x value. So if we go y is equal to -3, we're shifting over 3 values, so our graph would look something more like this here. And if we did a positive value of h, say as 5, we'd be shifting over 5 values to the right side. So we'd have our point there, and it would decrease that way and increase to the left. And if we change our value of k, k is going to denote what we change on our y-axis. So say we put a k is equal to 3, we'd be going up 3 values, which would be here, so our graph would look something like this. In terms of our domain and range, we're actually going to be seeing the same thing. For our domain, it's going to be all values of x and -x, so we'd be seeing -infinity to +infinity for this. And again, we have that asymptote of y is equal to 0. So it is approaching 0 as we go to the right or as we increase positively. And you'll see that actually if we go to -x, we see that y is increasing to infinity. So again, this is going to be from 0 to infinity. Now we call this function, because it has this decimal or fraction that's in it that's less than 1, we call this an exponential decay function, which we can use for solving word problems as well. So now this brings up, how do you solve equations where you're solving for x? So say for instance we have 2 raised to the x, and that's equal to 2 raised to the 3rd power. Well, when this happens, we actually can ignore what the base value is, and we can focus on what the exponents are. Because our base values are the same, we would see that y is equal to 3. Now moving this to the next step, what if we had 2 raised to the x, and that's equal to 8 raised to the 3rd power? Well, we need to change the base to be the same value. So we know 2 to the x, and we can actually make 2 into this 8. We know that 2 raised to the third power would be 8, but then we're also raising that to the third power. So that whenever we have an exponent raised to an exponent, we're actually going to multiply those two values. You don't raise those two exponents together, it'll just be multiplying. So 3 times 3, and that's going to be equal to 2 to the x. We know that 3 times 3 is going to be 9, so that's going to be 9 here. So then we'd have x is equal to 9. Now say, for instance, we have 9 raised to the 2x plus 1, and that's going to be equal to 3 raised to the 6x. Well, we can do the same thing with this 9. We know that 3 raised to the second power will be 9, so we can actually take that 2 and put in parentheses 2x plus 1, and that's going to be 3 raised to the 6x on the other side. Well, now those 3's we can ignore and just focus on what's in the exponents because our 3's are the same value. So we'd have 2 in parentheses 2x plus 1 is equal to 6x. We can multiply this out, these two values, so we'd have 4x plus 2 is equal to 6x minus 4x on this side. This will give us 2 is equal to 2x. Dividing by 2 on both sides will give us that x is equal to 1. Now what if we have inequalities? Say we have 16 raised to the 2x minus 3, and that is less than 8. Well, with 16 and 8, we would need to simplify that into something of 2 raised to a power. So that's 2 raised to the 4th times 2x minus 3 is less than 2 raised to the third power. Now that we have our base the same, we can change this to looking at what's in the exponents. So we'd have 4 in parentheses 2x minus 3 is less than 3. Multiplying this out, we get 8x minus 12 is less than 3. We would move 12 to the other side. So this would give us 8x is less than 15. Divide by 8 on both sides. So we will get x is less than 15 over 8. Now let's say, for instance, we actually have 2 raised to the x plus 2 is greater than 1 over 32. Well, if we remember, we can think of these fractions in terms of individual components which we would be raising. And we know that we have base 2 over here, so there has to be a fraction in which we can get to 32, which is going to be 2 raised to the 5th power. And we can put 1 raised to the 5th power here. So this would give us actually 1/2 raised to the 5th power. However, 1/2 is not the same as 2. So what we can end up doing is putting a negative in front of this. And if we do that, we would actually be flipping whatever's negative flips what's inside of this. So that would make it 2 to the 5th. So just remember, any sort of negative you see in front just means that you flip what's inside. You do the reciprocal of what's in that. But since we have 1/2 raised to the 5th, we actually need 2. So 2 raised to the negative 5th would be the same as 1/2 raised to the 5th power. So that tells us that we have 2x plus 2 is greater than 2 raised to the negative 5th, which therefore we actually get that x plus 2 is greater than negative 5. So x would be greater than negative 7 in this case. So let's move on. Let's take a look at this word problem. Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. What is the equation of this exponential growth? And how many bacteria cells can we expect after 12 hours? So we're going to solve this first problem right here. We're going to figure out the equation. So again, the standard equation that we're going to be looking at is a b raised to the x power. And in this case, a is going to be our initial amount that we have. Our final amount will be what's here in y. And usually for x, it's going to be in terms of time. So with this information, we know that the final amount is 23,000 cells. We had an initial amount of 7,500 cells. And b, we don't know, but we know that their time is going to be for 4 hours to go from 7,500 to 23,000. So with that information, we can solve for b. So what we want to do is we want to get b by itself. So what we'll do is we'll get everything else, move it to the other side. So if we divide by 7,500, we're going to get approximately 3.067, and that's going to be equal to b raised to the 4th power. So for us to be able to solve for b, what we can do is we can take something called the fourth root, or we could do this where we actually raise it to the 1/4 power. And if we do it to that side, we'd have to do it to the other side as well. So anytime that we take something like b raised to the fourth and we raise it to the 1/4 power, again, whenever we have an exponent raised to another exponent, we can just multiply those values. So b to the fourth times 1/4. Those will actually cancel each other out. 4/4 is going to be 1. So we just get b to the 1, which we just call b. So those are going to cancel out. And if we take the value of 3.067, raise it to the 1/4, we would get that b is equal to 1.323. So that would tell us that our final equation is going to be equal to y of 7,500 times 1.323 raised to the x power. So now that second part of the equation says what happens after 12 hours? How many cells are we going to have? So we can plug that into our equation now. So we'd have 7,500 of 1.323 raised to the 12th power. And if you use your calculator to solve that, you would have a total of 215,665 bacteria cells. And that'll be your final answer.